All right, welcome back. So today we are going to discuss the technique of partial fraction decomposition. Admittedly, this is this is an extremely technical technique. There's a lot of particulars along the way. So we're going to break this down into 3 videos. So one, this is just going to be the overview, and then we're sort of going to break down step 1 and step 2 of the process individually in its own right. But one nice thing about partial fraction decomposition, despite the large number of technicalities, is that the form of the functions where partial fraction decomposition applies are actually not all that wild or crazy. They're just rational functions of the form polynomial over polynomial, a classically important collection of functions in mathematics. So an example of such would be like this x squared minus 4x plus 10 over x plus 1 squared times 2x minus 3. So this function, you can see quite clearly there's a polynomial upstairs, x squared minus 4x plus 10, and downstairs you have to FOIL everything out and do all the distributive property, but if you did, you'd get a degree 2 thing times a degree 1 thing, ultimately a degree 3 thing downstairs. I will make a note here, in order to utilize the technique of partial fraction decomposition, you've got to have a numerator degree less than the denominator degree, so upstairs degree less than the degree downstairs, and if you look at this example, that would hold. We've got a degree 2 upstairs and a degree 3 downstairs. Should you have an equal or higher degree upstairs, you'd have to use polynomial long division initially. Not really a point of emphasis here, but the overarching idea is the partial fraction decomposition is sort of based on having a polynomial or a polynomial. We're denominator heavy with a higher degree. But yeah, so be it. So the idea with integrating such functions, because like you could imagine trying to integrate this function that's in this bubble, like not so easy to do in one piece. However, we use an algebraic decomposition to ultimately break our function into bite-sized pieces. So say you've got this function here, note degree 1 over degree 2. Downstairs, each of the factors is just a degree 1 factor. Well, we're going to decompose into a pair of fractions, each fraction over the individual degree 1 factors that were downstairs below, and then upstairs, to be consistent with our theme of numerator degree less than denominator degree, we're going to have just a number upstairs. So throughout here, the A, B, C, and D that you'll see within these decompositions are just numbers. And by the way, each of these forms that we'll be going through, the form of these decompositions is really just something at this stage in our development to be memorized. While you can use linear algebra to demonstrate exactly why each of these decompositions would be valid, frankly, even in a first semester linear algebra class, that's not a common topic of study. So this is the math behind this is somewhat sophisticated, but the point is that the decomposition itself is doable, provided, say you've got 2 factors of degree 1 downstairs, you just break each of those degree 1 factors down into their own individual fractions with degree 0 constants upstairs. What about this second example? We also have degree 1 factors downstairs, but one of those degree 1 factors is repeated multiple times, in fact 3 times over. Well, if you have a factor that's repeated 3 times over, you'll essentially just need 3 terms in your decomposition accordingly. So we have an x minus 2 cubed over here. As a result, within our decomposition, you'll need an x minus 2, an x minus 2 squared, and an x minus 2 cubed along the way. Just numbers upstairs because we're building this off of a degree 1 factor below. So this is another common decomposition. You should certainly be familiar with each of the 3 decompositions that are listed here, despite the fact that it takes just memorization sort of to get familiar. Now, as far as this last example, what you might note is that we've got a factor of x squared plus 4 here. Now, in principle, you might think, ooh, that x squared plus 4, maybe I can break that down further into more bite-sized pieces. Maybe I can take that degree 2 polynomial and factor it down to degree 1 polynomials. Well, check out over here. If you did try to take x squared plus 4 and break it down into a pair of degree 1 factors, you would actually have to invoke I, the square root of minus 1, a complex number. And this is a little bit of a challenge, or a problem, I guess, an issue, if you will, because when we're looking at our functions in this course, we're normally thinking of the inputs as just real numbers. We're normally just thinking of like the horizontal axis being composed of just real numbers, and well, hey, then invoking complex numbers would sort of be a violation to that. So should we see a factor of the form like x squared plus some positive number, really there's no way to factor that further using real numbers, and as a result, we'll just sort of leave that degree 2 factor in the form that it is. We say such a form is an irreducible degree 2 expression because, well, you can't reduce down further to a product of degree 1s. But that being said, if you do have an irreducible degree 2 factor, the form of its decomposition would be putting that degree 2 factor downstairs and then writing a degree 1 factor above it, the bx plus c. Note, this is consistent with the theme of numerator degree being less than denominator degree. If the denominator is of degree 2, then the numerator could be of degree 1, and that's where the bx plus c comes from. The x plus 1 that was downstairs, as we've seen before, when you just have a single factor of degree 1, you throw a constant upstairs. So again, get familiar with these forms of decomposition when you just have degree 1 factors, when you have degree 1 factors repeated, and when you happen to have degree 2 factors. These are, well, they are what they are, but they're a component of sort of the training regimen to being able to tackle a partial fraction decomposition exercise. Now, as mentioned initially, the idea of decomposing is so that the resulting functions within our sum of our decomposition are going to be easier to compute integrals of. And so if we look at some of the resulting pieces that occur, what if we had like a over x minus 2? Well, that's a degree 1 thing downstairs. The a that's upstairs you could just factor out. And so really you could think of integrating a over x minus 2 is really no harder than just integrating 1 over x minus 2, or in general, integrating 1 over mx plus b. If you used a u substitution with u equals mx plus b, you'd ultimately get to the expression 1 over m times ln absolute mx plus b. So to do this technically, we're using the substitution u equals mx plus b, and that's actually where the 1 over m comes in, because when you compute du, you'll get m times dx, which means dx is 1 over m times du, and that's where the 1 over m comes from. So if you want to sort of sanity check yourself and just run a derivative here, of course the c would drop out. When you take the derivative of the ln absolute mx plus b, you'll get 1 over mx plus b times m using the chain rule. The m that you multiply by neutralizes with the 1 over m that's in front. So you'd get 1 over mx plus b as you would hope. Another form that pops up when you have the repeated factors is a degree 1 thing raised to a power. So what if you had a degree 1 thing raised to a second power? It would be analogous if you had it raised to a third power. But yeah, raised to a second power, you could almost think of this as like this thing to the minus 2 power, right? And if you actually use the identical u substitution, u equals mx plus b, you'd end up with what? That thing to the negative 2 power, use the power rule. The power would increase to a minus 1, and then you'd put a 1 over minus 1 in front, which would put this negative. But then you also have the factor of 1 over m as a result of your u substitution. So the long story short is, though, expressions of this form are integrable. If you had a 3 here instead of a 2, you'd have a minus 2 here, and then you'd have a minus 1 over 2m whenever you would sort of have to, when you would have divided by that power of minus 2. So that would be an adjustment there. Maybe I'll throw that in here so you can see it. If this was a 3, this would be a 2, and then you have a 2 down here from using the power rule. But the long story short is all integrals of the form 1 over degree 1 polynomial raised to a power are integrable with just u substitution. Not too bad. What about this case where we had the degree 2 factor downstairs? Well, in general, I'll just write that degree 2 factor as x squared plus a squared, where a was just any number. In this case, the a would be 2. But because, well, a squared would be 4, right? But now, the x that's upstairs, you could take this x squared plus 4. Let me just write it out so that you can see this. You could take that a over x plus 1 and just leave it be. But if you wanted to, you could write the bx over the x squared plus 4, and then write the c over the x squared plus 4. And if you did, well, the bx over the x squared plus 4, you could factor out the b and essentially get to this form. Now, this form is actually not too bad. This is classic u sub, because if you let u equal x squared plus a squared, the du is just 2x dx, which is just a multiple of the x dx that you see. So, hey, that works out really nicely. And then downstairs, this may be the quirkiest one of all. Stay tuned for the future video where we break down this step 2 in more detail. But 1 over x squared plus a squared dx. Here we're going to use a u substitution with u equal x divided by a. Ultimately, this is going to relate to the tan inverse. If you remember, tangent inverse has a derivative of 1 over x squared plus 1. And so x squared plus a squared is almost x squared plus 1. And so ultimately, our integral here is almost just the inverse tangent function but we need this substitution to pull it off. Stay tuned for a future video for that. But the big picture here again is that even in the case of the c over x squared plus 4 like we have here, or in general factor out the c, 1 over x squared plus a squared, you have an integrable piece that results from your decomposition. So we're going to take polynomials over polynomials, we're going to decompose them into bite-sized pieces, and then we're going to integrate each of those bite-sized pieces. It's a lot to keep track of mentally because you've got to remember the decompositions. It's a lot to deal with in terms of the integration because there's a lot of different forms in which those integrals of bite-sized pieces result. But provided we keep track of all of this, we can deal with the integration of a gigantic collection of functions. And this is a victory of thought, considering how important this collection of functions is to mathematics. So I'm going to stop this video here for today, and then we're going to dive into the algebra, dive into the calculus that's associated, and then put together ourselves a suite of videos associated with this topic.